Hello friends, in this video we are going to discuss about the semiconductor phenomena when incident of light happens. Let us consider semiconductor. So it is a semiconductor but and light will incident on this semiconductor like this. This is the light that will incident on the semiconductor. So I can write that light is incidenting on this semiconductor. Now, for this case, let us consider that the wavelength of the light that is incidenting on the semiconductor is lambda. Now, according to the wave particle duality, this light that is incidenting on the semiconductor is nothing but an electromagnetic wave. So we can say that according to wave particle duality, the incidenting light is nothing but a electromagnetic wave. And from wave particle duality, we know that a electromagnetic wave is associated with photon particle stream. So we can think that this light which is incidenting on the semiconductor is nothing but some photon particles. So these are nothing but some photon particles. Now let us assume that the energy of each photon particle is capital E. So we can write it as E of photon. And we know that the photon particle will have energy equals to E photon, that is equals to h into nu, where nu is the frequency of the light, or we can say that nu equals to c by lambda, where the c is the speed of light and this lambda is the wavelength that we have assumed. So far we have got that the photon energy of each photon particle is h nu. Now, when these photon particles will incident on this semiconductor, then these photon particles will be absorbed or it can transmit throughout the semiconductor. So there are two possibilities that can take place, that the photon particles after incidenting on the semiconductor, either they can be absorbed or they can be reflected and transmitted. These are the two possibilities that can happen when a photon particle will incident on the semiconductor. Now, if the photon particle energy, that is the if E photon, is greater than or equals to the band gap energy of the semiconductor, that is Eg, then the photon particle will be absorbed. That is, we can say that photon will be absorbed by the semiconductor, that is photon absorption phenomena will take place. And if the E photon, that is the photon energy of each photon particle, is less than Eg, then the photons will either be reflected or transmitted through the semiconductor. So this is the condition. So this condition, when the energy of a photon particle is greater than the band gap of the semiconductor, then only the photon absorption takes place. So we can say that if the energy of the photon particle is greater than the band gap of the semiconductor, that is Eg, then only the photon particle absorption will take place. So from this equation I can say that E photon is nothing but h into nu, where h nu is the frequency of the light and h is the Planck's constant. Or we can say, if I put the value of nu equals to c by lambda, where c is the speed of the light and lambda is the wavelength. So if I put the value of c and h, so we can say putting the value of c and h, we can say that lambda can be written as less than equals to hc by eg. So this is the lambda of the light that will be absorbed by the semiconductor. Now if I put the value of c and h in this equation, so I can write that it will be, if I put the value of h, we know h equals to 6.6 into 10 to the power minus 34, and c value is 3 into 10 to the power 8, and eg value is, if I convert the eg value from electron volt to the joule, then it will come as 1.6 into 10 to the power minus 19, and there will be eg. Okay, so this is the equation where we can find the value of, in this way we can find the value of lambda. So after calculating, there will be a 10 to the power 6 also. So after calculating this total equation, we can find it will be 1.2376 divided by Eg, and this Eg is right now in electron volt, and the unit will be micrometer. So we can say that if we want that the photon will be absorbed by the semiconductor, then we need to incident such light which has a lambda in micrometer, and this should be less than equals to 1.2376 divided by Eg, where Eg is an electron volt. So this is a monitoring equation by which we can find which wavelength of the light will be absorbed by the semiconductor. And this is a very important equation with respect to the gate numerical. So we can see here from this equation that the maximum value of the lambda that will be absorbed by the semiconductor will be 1.2376 divided by Eg. So this is the maximum value of lambda that will be absorbed by the semiconductor. And this maximum value of lambda is called the critical wavelength of the semiconductor. Critical wavelength of semiconductor, or we can say lambda critical. So this is the critical wavelength of the semiconductor. That means this is the maximum wavelength that can be absorbed by the any semiconductor. So for this case, in the gate examination, generally they ask the critical lambda question. They give you the data about the Eg and they will ask the critical lambda. So in this case, there are some point that should be remembered by the students like this, and I am writing those in the key points. So the first key point that should be remembered, that wavelength of visible light. What will be the wavelength of a visible light? Generally, the wavelength of a visible light is from 0.38 micrometer to 0.76 micrometer. Next, any wavelength of the light, any wavelength of light which is greater than 0.76 micrometer, that belongs to infrared light. So this is the two information that should be needed during the numerical questions in the GATE. So this is all about the critical wavelength of semiconductor when a light will incident on the semiconductor. Thank you.